In a bulk material, there are 10 to the 23 to 10 to the 27 atoms. If we try to model it directly, even with the best algorithm and the fastest supercomputer, it's still going to fail. Some researchers try to model a scaled-down version of the sample containing a few hundred atoms, but nanomaterials have different properties to bulk materials. Is there any trick to model bulk materials without losing accuracy? If we zoom into the bulk material, we can see that atoms are arranged in a translational invariant manner. This symmetry could help us to reduce the simulation window significantly. In this video, we will look at how to represent material modeling problems using linear algebra, and we will demonstrate the trick of solving the problem from a purely linear algebra perspective. The matrix we are looking at in this video is called Circulant Matrix. In this matrix, we can obtain each successive row by taking the preceding row and cyclically permuting it to the right. One special property of a circulant matrix comes from multiplication with another vector. Consider the expression to compute the zeroth entry of the matrix vector product. If we want to compute the first entry, we don't need to rewrite the whole expression. Instead, we can rotate the A, B, C, D, E stuff one element down. Now I want to avoid calculation. I wonder if there are any vectors we can rotate easily. First, let's consider an arbitrary vector. We can multiply it by a constant, multiply it by a matrix, and add it to another vector. Now matrix multiplication is trivial, as we can cyclically rotate every vector with a permutation matrix. Vector addition is also trivial, as we can add the difference before and after index rotation. Hence, scalar multiplication is the only option left. Now the easiest way to rotate numbers is to multiply them with another number omega in the complex unit circle. Let's visualize the complex numbers with vectors of different colors in the complex plane. If we take these different colored numbers generated by multiplying the zeroth number with omega repeatedly, we can multiply them simultaneously with this yellow-colored complex number. Is this a vector that can be cyclically rotated easily? No, because when we rotate this vector by the yellow-colored complex number, we get arrows all around the complex plane. In particular, if we apply the inverse of yellow number to the zeroth entry of the vector, it does not end up aligning with the last number. Remember, we want the zeroth entry to have the last entry value before rotation. Now this time, let's try making the zeroth entry of the vector 1 and set the angle of rotating number to be 2 pi over 5. As 5 is the number of entries in our vector. This time, when we multiply the vectors by the inverse of omega, the entry matches exactly the preceding entry. Is it the only vector that we can rotate easily? No, because we can also choose the angle of omega to be 4 pi over 5, and everything works as well. In fact, for an n-dimensional vector, we can construct these vectors containing power of different omega, for all omega equal the set shown on the screen. We can rotate the vector constructed downward by multiplying omega inverse. We can rotate it upward by multiplying by omega. Now, I will claim that this is the eigenvector of the circulant matrix. Let's define omega Mn to be the mth root of omega to the power of n equals 1. We want to prove that the vector containing the omega stuff is the eigenvector. First, let's compute the dot product between the zeroth row of the matrix and the vector, and let's call it lambda. When we go down to the second row, the ABCDE in the square bracket stuff gets cyclically shifted downward by one index. Now we know that multiplying by inverse of omega m5 shift the omega stuff in the square bracket downward by one index. Now both ABCDE and the omega stuff were shifted downward by one index. The expression in the square bracket is also lambda, leaving a residual term of omega. Now moving down to the next row of matrix. Using the same technique as before, the residual term now becomes omega squared. Each time we move down the matrix by one entry, the dot product gets an extra omega term. Comparing the matrix vector product and the vector, we see that every entry gets multiplied by lambda, and hence the omega vector is the eigenvector with eigenvalue lambda. Note that I have set the zeroth entry to 1, hence the product between the zeroth row and the vector is the eigenvalue. Now if we plot the real part of all eigenvectors, we can see that they look like waves. The process of obtaining all eigenvectors is just Fourier transforming the first row of the matrix. This can be done with O n log n. I am not going to the detail of Fourier transform, but if you want to know more, there are plenty of resources online. The postulate of quantum mechanics says that any observation and measurement of a quantum state can be represented as a Hermitian matrix. That is, the complex transpose of this measurement matrix is equal to itself. The quantum state that we observe can be represented as a vector. The eigenvalue of measurement matrix is the possible outcome of these measurements. The most important quantity we want to measure is the energy of the state, because it somehow determines the product of chemical reactions. We are looking at Schrodinger's equation in the tight binding picture. In this picture, we represent the wave function in the basis of atomical orbitals. Here I have drawn the shape of the s orbitals, the p orbitals, and the d orbitals. Usually, a basis of 9 dimensions is sufficient to describe one atom. One special property of this basis is that two basis functions belonging to different atoms or orbitals are orthogonal. These basis functions are termed maximally localized linear functions. We also represent the energy operator or Hamiltonian as a tight binding matrix, as shown on the screen. I am going to explain this equation using an example. Let's look at a system with just two atoms. Each has one p orbital. We can represent this system by a two-dimension vector. The Hamiltonian of this system can be described as a 2x2 matrix. Recall our tight binding equation. The first term is the on-site energy. It's associated with the electron orbiting around the ith atomical orbital. This goes to the ith diagonal. The second term is called the hopping energy. It associates with the electron jumping from the jth atomic orbital to the ith atomic orbital. It goes to the ith row, jth column. Note that the on-site energy depends on the nature of the orbitals. The hopping energy depends on the direction between the atoms and the combination of orbitals. Now we have got the algorithm for obtaining the Hamiltonian matrix. Let's ask ourselves, when does the matrix become circulant? In one case, a linear chain of atoms with periodic boundary conditions can be represented as a circulant matrix. In fact, you can think about it as a ring by wrapping and connecting the endpoints of this linear chain. One famous example of this system is the benzene ring. Benzene ring consists of 6 carbon and 6 hydrogen. Each carbon forms 2 bonds with its neighboring atom and 1 bond with hydrogen. It is sufficient to ignore these electrons. We want to model the energy of the pz electrons that form the delocalized pi bond. Now let's view the benzene ring as a 1D periodic chain. Looking at the zeroth atom, it has an on-site energy of epsilon, and it has 2 neighbors, the first atom and the fifth atom. The researcher shows that hopping decays exponentially with distance, so we only include the nearest neighbor hopping and set it to t. Similarly, the first atom has 2 neighbors, the zeroth and second atom. By symmetry, the on-site energy is epsilon, and the hopping energy is t. The second to fourth atom behaves similarly to the first atom. The fifth atom has 2 neighbors, the fourth and the zeroth atom. The on-site energy is epsilon and the hopping energy is t. We set all other entries to 0 for simplicity. As discussed before, we can consider just the 0th column or 0th atom. We collect the on-site and hopping, absorb the phase of the 5th atom and 1st atom to the hopping, and sum them together. Using the Euler's identity, we see that the case eigenvalue is equal to epsilon plus t cos kr, where, as the convention by physicists, k equals 2m pi over L is the wave vector, and r is the distance from the 0th atom. There is a problem with this method. Let's return to our diatomic toy model. Suppose we add another s orbital to each atom in this model. Then the tight binding energy matrix looks like this. It is no longer circulant. This problem is fatal because we cannot accurately model an atom with just one orbital. To model atoms, we have to generalize our circulant matrix theory. Now let's look at our circulant matrix. Instead of complex numbers, we replace it with the other unknown number field. Is our algorithm still going to work, or at least partially work? What kind of number field do we want? Let's look at the energy matrix of the diatomic system. If instead of treating it as a 4x4 matrix, we treat it as a 2x2 matrix of 2x2 matrices, then it is a circulant matrix. Similarly, since we can multiply matrix with vector, we can rearrange the 4D vector as 2D vector of 2D vectors. Now let's return to our problem of 5x5 circulant matrix and set the unknown field to matrix and vector. What does the eigenvector of block vector look like? It should work no matter whether the matrix inside the block vector or matrix is 2-dimensional or 2-million-dimensional. This means that the plane wave solution, if it exists, must oscillate at a period of 5 times the length of the vector. Let's, without loss of generality, assume that all numbers inside the vector have the same phase omega. Then we can apply the trick we developed in the circulant vector section, where in this case, we let the vector be fixed and rotate the omega stuff that act as a phase in this time. We again find that each time we cyclically rotate the matrix by one entry down, we obtain an additional residual of omega. But there is one thing that we need to be very careful. When we come to the final step of Fourier transforming the matrix, this equality does not necessarily hold for all vectors. Instead, we have to find the solution to this equation by diagonalization. Using all the theory above, let's look at graphene. Each unit cell contains 2 carbon atoms and a few bonds that connects between the 2 atoms and the neighboring unit cells. We normalize the unit so that the carbon bond has a unit length. In this problem, we only include one pz orbital per atom. To connect to the previous theory, we can also think about the unit cell as one atom with 2 orbitals. We define A1 and A2 to be the lattice vectors. We can generate the whole lattice by translating integer steps in the A1 and A2 direction. Note that in the lattice, we apply periodic boundary condition in A1 and A2 direction. And I will use round bracket to represent the lattice vector and square bracket to represent the Cartesian vectors. Now I am going to prove that the eigenvector looks like plane waves. The first step is to define the position of each atomical orbitals in the vector. The algorithm was shown in the screen. The advantage of this algorithm is that if we group this vector to a vector of vectors, then each vector of vectors representing neighboring row of atoms is arranged as neighbors. Inside the vector of vectors, each vector representing neighboring unit cells are arranged as neighbors. And inside these vectors, the 2 orbitals in the same unit cell are neighbors. Now let's look at the hopping value of graphene. Note that I have set the on-site energy to 0 as all graphene orbitals are identical. We pick a random unit cell located at ij in the lattice coordinate. The 4 neighbors are shown on the screen. The 0th atom in this chosen unit cell has 2 nearest neighbor first atoms in the neighboring unit cell, and the first atom in the same unit cell is also its neighbor. Similarly, the first atom in this chosen unit cell have 2 neighboring 0th atoms in the neighboring unit cell, and the 0th atom in the same unit cell is also its neighbor. If we treat the hopping between unit cells as a matrix, our chosen unit cell has 4 hopping to the up, down, left, and right neighbor. It also has an on-site matrix representing the intra-unit cell hopping. Let's construct the matrix of matrices that represents the on-site and hopping of each column. The diagonal or on-site term represents the hopping within this layer. One thing to note is that it is a block circulant matrix. The subdiagonal contains the hopping to the right column matrix, and its numerical value is shown here. Due to periodic boundary condition, the top right entry also have this hopping. The superdiagonal contains the hopping to the left column matrix. The bottom left entry also contains this term due to the periodic boundary condition. All other entries are zero. It is clear from the argument above that the hopping matrix between layers is a circulant matrix. Hence, we can write the second to the last entry of the eigenvector as the first entry times the phase factor. Now we take the first row of matrices and multiply it with vector. We get the expression shown on the screen. Noting that the unsigned matrix, the hopping to the left column and hopping to the right column matrix are all circulant up to the unit cell level. If we take the linear superposition of circulant matrices, we end up getting another circulant matrix HKA2. Hence, the vector representing the whole column has the plane wave structure. In other words, when we look at the eigenvector, we only have two independent numbers, C0 and C1. The rest are just phase factor. To determine C0 and C1, let's investigate the unit cell at the 0th row and 0th column. It does not have any phase factor. It has four neighbors. Each neighbor has the following hopping term shown on the screen. We let the hopping matrix absorb the phase, and then we sum them together. We get the following matrix. Before diagonalizing this matrix, we investigate the k-vector that we can choose. Due to periodic boundary condition, we want the k-vector to satisfy the following relation. We want to write k in terms of something that can help us to filter ij, big I, big J. We construct B1 to be a vector perpendicular to A2 in the xy plane, and we construct B2 to be a vector perpendicular to A1. We set the magnitude of B1 and B2 so that the dot product between B1 and A1 is 2 pi. The dot product of B2 and A1 is 2 pi. K is a linear superposition of B1 and B2. We want the exponential of K dot position to be the right-hand side to match the solution to the circulant matrix. Comparisons show that we can choose the following alpha and beta value. With this in mind, we diagonalize the K matrix using standard linear algebra approach and a lot of simplification. One thing to note is that Kx is the Cartesian x component of the K vector. Ky is the Cartesian y component of the K vector. And our final expression for all possible energy is shown by this expression. Let's plot this expression. The upper surface corresponds to taking the plus sign before the square root, and the lower surface corresponds to taking the minus sign. This energy diagram helps explain a lot of phenomena of graphene observed experimentally. For example, researchers find that no matter what impurity you dope, such as crap, you will always get a large enhancement of conductivity. This is because all electrons in graphene occupy the lower surface, and there are almost no state above it. If you dope something, you are changing the level of highest occupied molecular level, or precisely the Fermi level. There are more states for electron to move. How to generalize our theory to model other materials, such as 3D materials? In general, the hopping term depends on the distance between two atoms, and the direction cosine between two atoms. It is shown by John Slater and George Coster that the hopping has the following expression. I have written a few here. Please refer to their paper for the full list of expressions. Here, L, M, and N are the direction cosine to the x, y, and z axis, respectively. At this stage, you might wonder, is there any researcher who successfully discovered some new material using tight binding model? Yes, in 2011, Rafi Bristol and Alan MacDonald used a modified version of tight binding model to model a twisted bilayer graphene. They predicted that if the twist angle is equal to 1.05 degrees, something magic is going to happen. 7 years later, Yuan Cao and Pablo Yalilo discovered unconventional superconductivity and associated insulating state in this magic angle. Overall, material modeling is becoming increasingly important in scientific research. I hope this video gives you a feeling of what a theoretical material scientist is doing, and appreciate the importance of mathematics in material modeling. If you want to see more topics that connects material and mathematics, please subscribe to this channel.